talk to you a bit about Fractal, our open source framework for reproducible bioimage analysis at large scale using OME-Zarrs. This last part really being the connection to today. And Bura gave an introduction to OME-Zarrs already. I'll give a bit of our perspective of how 3 years ago we landed on OME-Zarrs and said, no, we really want to build our framework all around this before I'll dive in to explain how we do the reproducible image analysis and how we scale it up. So as you're likely all aware, given that you're in this call, modern microscopes produce a ton of data, and that can be a struggle. It can be a struggle to know what to do with. Specifically, back in my PhD days, that could mean walking into the lab in the morning, and overnight the microscope had generated, let's say arbitrarily, 163,518 images. And sure, I could open every one of them individually, and if this was the general approach we'd take, I'd probably still be doing that today. Because what we really want to do when we have these large data amounts is make them accessible for much more interactive exploration and browsing, where we can have very zoomed out views, but we can also dynamically zoom into data and stream only what we need, both from the image data that we actually imaged, but also from results of processing that we created on them to verify, do our images look like we expect? Did our processing do what we thought it would do? And we want to be able to do this in an interactive fashion, a bit like Google Maps, so that we can really browse around those data sets, zoom out, compare different conditions, maybe zoom into something else, and explore what actually happens. This is a much more useful way of taking the same number of original images that the microscope created than if we'd open them one at a time, single gray channel, single plane images. So what do we need if we want to explore data that way? And we made a bit of a short list of the 3 key things we need from our data storage. Is we need data to be multi-resolution or have support for these pyramids that Puha mentioned before. This data really needs to be able to either live in the cloud or an HPC, because it just doesn't fit on a laptop anymore. And the data should be a format where we can store 2D data in, 3D data in, where we can put multiple channels in the same data set, and where we can have multiple time points in the same storage. And normally when I introduce it that way, I like to joke that, well, given that we have a specification, let's design our own file format. And it's a bit of a joke, but joke is it's not that arbitrary, because 5 years ago in my PhD times, that was my conclusion of, oh, I can use some HGF5 files and come up with my own way of using this that no one else knows how to read and do stuff with. And it kind of worked. It's just not a good idea. Luckily, we do not need to design our own file formats, because there is OME-Zarrs. And the OME-Zarrs really fulfill these requirements that we have for data storage of being pyramidal, being compatible with cloud and HPC, and something that we can have high-dimensional data in. But beyond just fulfilling the few spec items, the really cool thing about OME-Zarrs is the large community of people that put effort into building things around them. Puha showed these papers before, but the thing that always really impressed me was the diversity of viewers that exists, that allow you to view different kind of image data that's really optimized for EM, optimized for light microscopy, optimized for high content screening plates. And it's really nice that this ecosystem already exists. And this ecosystem actually goes beyond purely the viewers. We had this great hackathon last fall in Zurich, where we got a lot of people together to work on different parts of the OME-Zarr ecosystems, as illustrated in this overview on the right here. And we were planning to do a hackathon for 25 to 30 people. We couldn't say no to the 43 people that all had such cool things they were doing in the community, because from the people working on the Java side, to the people working on Python, to people working on the core spec or extending the spec or building new workflows in the OME-Zarr world, there's a really big drive of people building things. So if you want to pick a file format and you have somewhat of a choice to make today, this is a good choice. Now, let's assume we are all in this OME-Zarr world and we all came around to this next generation file format. The question we ask ourselves is, how do we solve this green part? Specifically, how do we run reproducible image analysis and at scale of terabytes, not just on a few megabytes or gigabytes, using these OME-Zarr containers? And the answer we've come up with for ourselves over the past 3 years is what we call the Fractal framework. And today I'll give you a bit of a context of how we built this framework, specifically what the different elements are that for us make working with OME-Zarrs interesting and where the specific benefits are from using these modern formats. So if we look at what the Fractal framework really is, fundamentally, it's a framework designed around processing OME-Zarrs. And the thing we've put in a lot of energy is a definition of what we would call like a task spec, we call it. It's our task, our processing units, our little Lego blocks that allow users to build workflows from existing pieces or to extend them with their own processing that they want to do to make sure that we're very flexible in what processing we enable. Given this Lego block tower constructions that we can build in the framework, we then have ways to run scalable executions of this on clusters. We have a web-based access for users, so they have an easier way of seeing their workflows, submitting them, seeing what failed, getting access to logs, all these kind of things. And when you can integrate with different OME-Zarr viewers at the back so that people can visualize their actual processing results. So I'll walk through a few of those different steps. We already heard enough about the spec of the OME-Zarrs, so I'll dive into this. What are these workflow tasks? For us, these fractal tasks are the fundamental unit of processing OME-Zarrs. All of them take data from an OME-Zarr, so in a standard format where every task knows how the data will be stored, and whatever parameters a user needs to provide. They do some processing, some image processing, some segmentation, some measurements, and they put the result back into an OME-Zarr container. Given that everything, once it's converted, goes OME-Zarr to OME-Zarr, these really become Lego pieces that are interchangeable, that you can use one, and then you can use another one that someone else built that works on the same standard data form. And over the past about 2 years or so, we've put in a lot of work to figure out how do we make it easier to build these units to people. And we've mostly done this in the Python space. Tasks aren't specific to be written in Python, but we've put in a lot of work to build tooling to make it easy for people to come up with their own processing tasks. Specifically, there's documentation and video walkthroughs of how this works. We have template repositories developed by Tommaso and Lorenzo that allow you to get all of the tooling around your actual code that would process an OME-Zarr easily. We have a library called NGIO that makes it easier to do processing operations on OME-Zarrs, to create new ZARs based on an existing ZAR, add labels to existing ZARs, or add measurement tables to ZARs that you have. And that's developed by Lorenzo here on the right. And with all of this tooling, we've seen a growing community of task developers and just packages coming up that allow users to do different kind of processing. We like to think of them in different categories. So sometimes what a task does is it converts data from some vendor format into an OME-Zarr. Sometimes we do things related to image registration, especially in the multiplexed imaging space, where we need to register 2 images or find corresponding objects in different rounds of imaging. We have different tasks that do segmentation, given an image, find your nuclei, find your cells, find other objects. Tasks that make different kinds of measurements of intensities, morphologies, textures, of how do we quantify what's actually in the images, and then a whole assortment of other tasks that do some processing with OME-Zarrs. And these tasks are organized in packages that different developers have built to do specific processing. And the easier way to show this is probably our overview page that I'll also put in the chat here in case anyone wants to check it out, which is the page where we list all of the tasks that people did, which is searchable, where you could browse all of the different categories. And you could see, is the thing that I want to do already packaged up by someone to run on OME-Zarr? And if we browse through this whole list, you'll see that they're sorted by packages. We can see different way of doing segmentation. There's currently 64 different task units that are available publicly. And you could, for example, say, well, I'm interested to do some segmentation. So I could do some blob detection. I could run cell pose model. I could run stardust. I could run some thresholding. Or you could come up with your own way of doing segmentation and packages up as one of these processing units. Importantly, I wanted to show this here. All of these processing units, they have extra information for what they're meant to, what their limitations are, what they can and cannot do. They also come with instructions on both how you would install them if you were using them in the Fractal context, but also how you would install them just in your Python environment, because all of these packages here are just Python packages that do some OME-Zarr processing that you could use outside of all of the rest that I'm going to tell you later on how we run things. These are just interoperable processing units that are meant to process OME-Zarrs. Now, instead of spending more time going over individual tasks and like telling you what that task does, I wanted to give you a bit of an example of the type of workflows we run with Fractal, and then point out where the OME-Zarrs actually come in very handy for doing these workflows. So we do a lot of processing of high content imaging data, especially screening related data, but doesn't need to be a whole screen. It can just be I imaged 10 or 20 wells on the multi-well plate. And typically the thing that comes off a microscope is a big pile of TIFFs or a big pile of vendor-specific formats. And the first thing we always do is we convert them to an OME-Zarr, because then we can use the same processing afterwards for a Yokogawa Cell Voyager, an MD Image Express, an Olympus Scan-R microscope, a different Leica setup. And we don't need to write our processing specific to the microscope anymore. We write our processing to work on this standard format. Once we have these nice OME-Zarr containers, something we often do is to say, well, we had some 3D data. Let's make some projections to have some easier overviews. And actually, sometimes these projections are really helpful for some processing as well. For example, we have data sets where people image organoids. And in this zoomed out view here, this is about 8 by 8 field of views of a microscope. But if you really zoom out, you just see, hey, randomly distributed over the whole imaging space, there are some objects, some organoids, and we can segment them using different segmentation models to find where in our big image, that is not just the individual fields that the microscope took, do we find our organoids. And then we can do measurements of them to figure out how many are there, how big are they, what features do they have. Sometimes that's just enough. But other times we really want to zoom in. So given that we have such structured data, we can then load every one of these organoids that we found in high resolution 3D. And if we try to do this for the whole well, we would just run out of memory immediately. But given that we found our organoids, we can just load a given organoid and then do single cell segmentation or nuclear segmentation in 3D and do measurements for those. Now, why is this valuable? For me, this image often illustrates it well. Here's some images by Silvia Barbiero from the FMI, where a given well can be fairly complex, have lots of organoids, but every one of these organoids is actually a complex 3D object that we want to do segmentation on, that we want to be able to interact with in 3D. And the OME-Zarr data structure really makes this much simpler. A few of the ways that it allows us to do this processing well is that given that we have pyramidal data, that's great for visualization, but it's actually also really useful for image processing, because in the first step, when we want to find object, we don't need a super high resolution image to just find where our objects are. We can do this at an optimized low resolution and save a lot of compute time. But then afterwards, when we say, good, in world coordinates, we found where our objects are, we can go and load those in high resolution 3D and iterate over specific regions of interest in the whole well to decide what we want to be processed. And the other big benefit is that we can then use this workflow both if we were processing data from one microscope, but also if data came from another microscope initially. We really get these interoperable units that aren't specific to a given workflow anymore. So that's a first view of like what happens on the content side of workflows, how we like build our workflows using these Lego pieces, and how people can extend them with the processing unit that they are missing. A big benefit of that is that often people can use 3 or 4 of the existing pieces and then add the one piece that they themselves need that is specific to their analysis. But once someone has built this Lego stack, this order of, yes, I want to do this and that processing, how do we actually run the workflows? So this comes to the workflow execution. And the way this typically works is that there needs to be a cluster somewhere that can do parallel processing. Typically, we've worked with Slurm clusters so far. And there's a Fractal server running that can talk to the Slurm cluster, submit a given workflow, manage what workflows the user has built, manage what packages are available, manages user access. Users talk to the server using a web client or a command line client, and then the server can submit workflows to Slurm, or we have ways that you can run these servers locally on your laptop, and then it just submits jobs to your laptop, so it processes it there. Importantly, in this whole setup, Fractal from the beginning was built with this federated logic in mind, where we don't expect people to send data for processing to Zurich. But the idea is that if a Fractal server is running in a given institution, it's accessible to people in that institution, and it has access to whatever cluster that institution is using. So we're running servers here in Zurich, we're running servers in Basel, and Fractal servers could be run in other places as well if people are interested. Now, from a user perspective, once someone has gone to the trouble of setting this up and configuring how it should talk to the HPC, people don't think about the server behind it. For them, Fractal is a web interface. They go to the Fractal website, they can manage all of their data sets and projects, and then within a given Fractal workflow, on the left here, you see the order of the Lego pieces of we want to convert some data, do some projection, do some segmentation, do some measurements in a very stereotypical example. And for each of those processing tasks, on the right, you get an interface where you could choose which model do you want to run on, what parameters should I specifically use for this task. Now, typically our users spend more time setting up this workflow than we're looking at here to like have everything configured, but at some point they're happy, they click submit the workflow, and it's getting sent off to run on a cluster. So now that workflow is running, we can monitor it, we can keep track, like, is it running? Has it run into an issue? What do its logs say? Get access to all of the different tasks that are on the server. And then over time, this workflow progresses depending on how big your data set is and how busy a cluster is on a given day. Step by step, they will finish. So here we converted the data, and we now have OME-Zarrs. Then we made the projection. We are running a segmentation model that may be running on GPUs on the cluster, if there's GPUs on the cluster. Once we have segmentation, we run some measurements, and all of this gets put back in the OME-Zarr. And given that it's a streamable OME-Zarr container, once processing is done, we can also go and look at those images that we just generated in a web viewer. So we can load up a given image set, and here we processed a small example data set of how things could look that then is interactive for people to look into. For this interactive view, we're using the VSAR viewer developed by Trevor Mantz, and he actually just added a really cool feature a few weeks ago, which is the ability to display label segmentations directly in VSAR as well, which makes it much easier for someone that runs a segmentation network to go into the web viewer afterwards and validate, did I have the right parameters? Is my segmentation looking as expected? Does it perform as well on condition number 3 as it did on condition number 1 that I tested it on? And this streaming, really makes this more accessible to people so that they run something from the web and validate right there in their web browser whether their processing actually made sense. Sometimes we actually become even more interactive with these OME-Zarrs, because the cool thing about these Zarr containers is that we now store the image data in them, we store the segmentation in them, and we store the measurements in them. So we can have workflows that make use of all 3 things. And for those, we typically go to the Napari viewer. And the Napari viewer can also visualize a whole plate of our images. So as shown in the beginning, we can browse, and we've built a series of plugins that allow you to navigate these plates, but also to say, given a plate that we have in an OME-Zarr, let's load additional data and correctly overlay it in the right space in the world coordinates. So for example, let's load some segmentation and measurements specifically for one of the field of views we had in this original data. And that will then stream this data directly here into the viewer, where we get access to the correctly overlaid segmentation of our images. But these segmentation now are also enriched with measurements we've made before. So we measured things about all of these objects, and we can then do things like color code objects by the measurements we made to explore all of the different things we measured and figure out what do they actually mean? Do they correlate with something we can visually identify? And sometimes this is just good for our intuition for our measurements. Other times we want to go a step further and say there are things that are quite easy for a biologist to annotate. In this case, I'll show an example of, can we find the mitotic cells? Typically, that's not hard for a biologist looking at the image to do, but it's not trivial to figure out how we'll tell the computer and like in the feature space, what really are those measurements. So we train interactive classifiers where we allow users to annotate a few objects of different classes. For example, annotate a few mitotic cells, annotate a few interface cells, and using all of the measurements that are behind this, that have been made before, we can train a little random forest classifier that tries to keep them apart. And this really makes use of this integrated structure and really organized data we have in OME-Zarrs, because we show the image data. We know when a user clicks somewhere what label this is related to, and given the label of segmentation, we can relate it to the measurements we've made before and then show results of such a model. And because we're in a viewer, this is also not just a one-shot training. We can iterate on this and correct mistakes that the training might have made until we have a model that we're happy with. And for me, that's one of the strengths of using these very structured data containers now that we can do with OME-Zarrs. If someone's curious to try this on their own, we actually put a lot of our example OME-Zarrs on Zenodo now in this collection. Oops, that I'll post in the chat as well if someone wants to check it out. So some questions. And the multi-well plate you saw before with, I think it's 23 wells with all of their segmentation and all of their measurements. So the one from this demo here is part of our public data sets. We share this. So if you want to retry the demo and see how it runs for you, all of that data is publicly accessible. That is hopefully an overview now of the different aspects of what you can do with processing OME-Zarrs and how we do this in Fractal. To wrap up, I'll give you a bit of context of where and how we're developing it. Specifically, Fractal is developed at the BioVisionCenter here in Zurich. We really aim to make state-of-the-art bioimage analysis at scale more accessible and to champion standards both on the image front, but also on the pipeline and workflow front on how we can do image processing. Now, Fractal development has been going on for about 3 years now. For us, importantly, is that all of this development is happening in the open. It's still actively being developed. We're still adding new features. We have big new features coming at the end of April to make the workflow interface more flexible and allow users to more easily test subset of workflows and these kind of things. And all of this development is happening under permissive open source licenses. So anyone who is interested in either a part of it or all of it is welcome to use it. You can use all of the different task packages on their own standalone without using the rest of the Fractal framework, or you can use the whole thing as an integrated solution using the servers and the web front end to allow more interactive workflow building and submissions. The important thing, if you want to try this, is that we're running this federated approach where every institution runs a Fractal server with access to their HPC. And as the BioVisionCenter, we partner with people that are interested to either get support on how to deploy it or support in how to use Fractal. Now, none of this work here that I presented today would have been possible without lots of people involved. Primarily of it's the whole BioVisionCenter team and all of the funding through the University of Zurich, the FMI, and earlier on CCI. But also all of the other people building things directly or indirectly for Fractal. So we work with a company called ExactLab to do a lot of the backend development. There's a big community of people building task packages that are public, and there's people building other things that are integrated into task packages, contributing to the plugins, or working on new task packages to come. And all of them really enable what we've been building here.